Hello everyone. First of all, I would like to sincerely thank our respected Vice Chancellor, Dr. Mohan and Dr. Jayanti ma'am for giving me this valuable opportunity to present my virtual lab project. I am truly pleased and grateful for their continuous guidance and encouragement. In this video, I will be presenting my project titled Line Coding Virtual Lab with PSD Comparison. This virtual lab helps students understand how digital data is represented and transmitted using different line coding techniques and how these signals behave in both the time domain and frequency domain. Now let us begin with the experiment. Aim. First, let us look at the aim of this experiment. The main objective of this virtual lab is to analyze and compare different line coding techniques and study their waveform and spectral properties. Through this platform, students can understand different categories of line coding such as unipolar, polar, bipolar, scrambling, and partial response coding. Generate line coded signals for a given binary input sequence. Observe both the input waveform and the encoded output waveform. And finally, analyze the power spectral density or PSD for each coding scheme. This allows students to visually understand how different coding methods affect bandwidth, synchronization, and DC components in communication systems. Theory. Now moving to the theory section, line coding is a process of converting digital binary data into electrical signals so that the data can be transmitted through a communication channel. Different line coding techniques represent binary data using different voltage levels and signal transitions. For example, in unipolar NRZ, binary 1 is represented by a positive voltage level and binary 0 is represented by 0 voltage. This scheme is simple to implement, but it produces a strong DC component and may cause synchronization problems when there are long sequences of zeros. In unipolar RZ, the signal returns to 0 within each bit interval. This increases the number of transitions and improves synchronization, but it also increases the required bandwidth. In polar NRZ, binary data is represented using both positive and negative voltages. This reduces the DC component compared to unipolar schemes and improves power efficiency. In polar RZ, the signal again returns to 0 during the bit duration, which improves timing recovery but requires higher bandwidth. Another important technique is bipolar AMI, where successive binary ones alternate between positive and negative voltage levels. This helps reduce the DC component and improves transmission efficiency. Self-synchronizing techniques like Manchester coding ensure that there is always a transition in the middle of every bit. This makes clock recovery easier but requires more bandwidth. Advanced techniques such as HDB3, B8, ZS, and Duobinary coding are also used in practical communication systems to maintain synchronization and improve spectral efficiency. Block diagram. Now, let us look at the block diagram of the system. The block diagram shows the overall flow of the communication process. It begins with a bit generator, which produces the binary input sequence. The data is then passed to the line coding mapper, where the selected coding technique converts the bits into a coded signal. Next, the signal goes through the waveform shaper, which generates the final waveform representation. After that, the signal passes through the clock or synchronization block, ensuring proper timing during transmission. The signal then travels through the communication channel, and finally the receiver makes a decision to recover the transmitted data. This block diagram helps us understand how digital bits are converted into physical signals for transmission. Procedure. Now moving to the procedure section. The steps to perform the experiment are very simple. First, the user enters a binary sequence or a random sequence can also be generated automatically. Next, the user selects a line coding scheme from the available options. After selecting the scheme, the user clicks the generate button. The system then displays the input binary waveform and the encoded output waveform corresponding to the selected line coding technique. After that, the power spectral density graph is generated, which shows how the signal power is distributed across frequencies. There is also a compare feature, which allows users to select two coding schemes and observe their waveform and PSD differences side by side. This makes the analysis much clearer and easier to understand. Pretest. Before performing the simulation, this virtual lab also includes a pretest section. The purpose of the pretest is to check the basic understanding of students regarding line coding concepts. The questions mainly focus on topics such as the drawbacks of unipolar NRZ coding, how binary data is represented in polar NRZ, which coding technique provides self-synchronization, how AMI encoding represents binary ones, and why scrambling techniques such as HDB3 and B8ZS are used. This helps students revise the theoretical concepts before performing the experiment. Simulation. Now we come to the most important part, which is the simulation section. Here we can observe how different line coding techniques generate different waveforms. First, we enter a binary sequence in the input field. For example, we may enter a sequence like 10, 10, 10, 11 and so on. Next, we select a line coding scheme from the drop-down menu. For demonstration, let us choose unipolar NRZ. After clicking the generate button, the system displays the input binary waveform. This waveform represents the original digital bit sequence over time. Below that, we can observe the encoded output waveform, which shows how the selected line coding scheme represents the binary data using voltage levels. For unipolar NRZ, binary 1 appears as a high positive level and binary 0 appears as 0 voltage. By changing the coding scheme, we can observe how the waveform structure changes. For example, in Manchester coding, each bit contains a transition in the middle, ensuring synchronization. In Bipolar AMI, the polarity of successive ones alternates between positive and negative voltages. This visualization helps students clearly understand the differences between various line coding techniques. Power spectral density. Below the waveform section, we can observe the power spectral density graph. The PSD graph shows how the signal's power is distributed across different frequencies. For example, in unipolar NRZ coding, we can notice a strong component near zero frequency, which indicates the presence of a DC component. Other coding schemes such as Manchester coding reduce the DC component but require more bandwidth. By observing the PSD graphs, students can understand the frequency characteristics of each line coding scheme, compare schemes. Another useful feature in this virtual lab is the compare schemes option. Here, two different line coding techniques can be selected and compared simultaneously. The system displays both the waveforms and PSD graphs for the two schemes. This helps students easily observe differences in signal transitions, bandwidth usage, and spectral characteristics. Such visual comparisons make the learning process much more effective. Post-test. After completing the simulation, students can proceed to the post-test section. The post-test contains conceptual questions related to the experiment. These questions test the understanding of concepts such as synchronization, DC components, scrambling techniques, and partial response coding. By answering these questions, students can evaluate how well they understood the experiment. Results and observations. From the results and observations, we can conclude the following. Unipolar coding schemes are simple but produce strong DC components. Return to zero and Manchester coding improve synchronization, but they require higher bandwidth. Bipolar schemes like AMI reduce the DC component and improve transmission efficiency. Scrambling techniques such as HDB3 and B8 ZS help prevent long sequences of zeros and maintain synchronization. Duobinary coding reduces bandwidth by allowing controlled intersymbol interference. Each coding technique, therefore, has its own advantages and trade-offs. Conclusion. To conclude, this line coding virtual lab provides a simple and interactive way to understand the concepts of digital communication. By visualizing both waveforms and power spectral density, students can clearly see how different line coding techniques affect signal behavior. This virtual lab effectively bridges the gap between theoretical learning and practical understanding. Once again, I would like to sincerely thank our respected Vice Chancellor Dr. Mohan and Dr. Jayanti ma'am for giving me this opportunity. Thank you for watching.